The rest of it was pretty fun still.
Oh, check it out. I want to see Barbarian.
What's that?
Oh, this looks really scary. It's out of the theaters right now. I like horror. I like horror films a lot.
Who wants to make a bet that in the last Halloween, Michael Myers will walk really fast?
Or at least get a scooter, maybe, you know?
Scooter.
Yeah. Some skates, some rollerblades.
Yeah.
Move a little faster. Yeah.
Maybe a new
Is he going to
mask.
be chasing Jamie Lee Curtis around while she's riding around on a scooter too?
She's gonna be in a walker. Yeah. All right. Let's. Okay. So I had a request to start our class with. Had multiple requests, at least 30, to start our class with mindfulness again. So we're gonna reinvigorate that. So let's just close our eyes and just sit up straight. And it helps to sit up straight because you're kind of kindling your awareness when you straighten your spine, let your shoulders just relax, fall down. Check your jaw. Are you holding tension there? Soften your eyes. See if there's any tension up in your temples. Just let that go. Tune into the display that's before you. You've got your eyes closed, but there's still light coming through the eyelids. And you might notice a shimmering. Just relax into that, like you were laying on your back in cool grass, looking up at the sky. And as you gaze into this shimmering darkness, your jaw is relaxing a little more. Your eyes are relaxing, softening. Noticing now the sounds in the room. Just letting those fall on you, impinge your eardrums. You don't have to do anything. They just come to you. As you find yourself drifting into thought, realize that's okay. You just bring yourself back gently, noticing your visual field, noticing the sounds. This is the game, just over and over, coming back and restarting. Beginning again. Let's come back carefully and gently. So maybe just move your feet, hands, move your body. And as you open your eyes, see if you can maintain that openness. Let the light of the world just flood in. That does. That was a good idea. That was a very good idea, ladies. Thank you. I'm actually starting to teach. I spent the summer doing a training with my Zen teacher to teach a meditation class, and I'm actually starting that this Thursday. I've got some students. We're going to meet on Zoom. They're actually ex-students. They're alumni from here. I got 3 of them who are going to be joining me for that. Hope to keep doing that. Wouldn't mind doing that for a living, but every other person in this area is running a yoga class or a meditation class. All right, my friends, there'll be no homework today. Josh said I shouldn't give any till Friday. We'll see. I'll see what I can do about that. I don't know if I can guarantee that, my friend, but I'll do my best. You can start it on Friday. If I give some on Wednesday, it'll be okay. We are going into our last application of integration. There's a lot of applications we could have done, but when I looked at the schedule, when you're in my classes, we just take time, right? We take the time we need to understand things. So over the weekend, I tossed some things out of our balloon. It's like, well, we won't be doing that. That's okay. So I picked the most important thing that I think we can do. And we're going to learn something about differential equations. Because as scientists, and most of you are scientists, this is the language of science. This is how scientists think in differential equations. And I hope you understand a lot more about them, even by the end of today, than you did when you came in. We're going to learn how to solve them, how to interpret them, understand them quantitatively and qualitatively. So first off, let's start with a classic one. This is Newton's law of cooling. Good old Newton. Really had his hand in everything. Newton's law of Newtons. Newton's law of cooling. I'm going to write it up and then we'll talk about what it means. This is a differential equation. So first off, T, this capital T, I made that very fancy. T of T is equal to the temperature of an object, some object, your favorite object, whatever it is, at time T. Whatever unit you want, you knock your socks off with that. You're a Kelvin person, go Kelvin, whatever you want. So that's the temperature, and T is our time, of course. I'm going to say that T naught equals the ambient temperature. So that's like the temperature of the room, the temperature that the object is submersed in. So let's say we've got here's our room, here's our object. Here it's got some temperature at time T, and then T naught is just what's filling the room. So maybe that's a potato in an oven, right? Looks like it. It's a potato in an oven, and the oven's set to temperature T naught, and it's already established that temperature, so it's been all preheated and everything. So what Newton realized was that the way the temperature of this object changed was proportional to the difference between its current temperature and the ambient temperature. So let's think about this. If this is a really hot, let's say this is 250 degrees Fahrenheit, sure. And I put in something that's at 0 degrees Fahrenheit, really cold. I've been freezing this thing and I put it in there. It's going to cool it's going to heat up really fast. And between 0 and 50 degrees, that's going to happen really fast. That's going to be a quick change. But as this starts to get closer to the ambient temperature, it's going to slow down how fast it's heating up. So the closer these two are in temperature, the slower the temperature change in my object. The greater the temperature gradient between the object and this thing, the faster the rate of temperature change. Does that make sense? This was what Newton observed. And then use the language of differential equations to describe that. So the rate of change of the temperature of the object with respect to time is equal to, and is proportional to, so I'm going to put a negative k here. This is just a proportional constant, proportional. And I'm going to say that k is a positive number, and we'll explain why the negative's there and everything. But this is your heating constant. This depends on the medium itself and the whole situation. So k varies with the situation, like the materials, etc. Changes from time to time. And then times the ambient temperature minus the temperature of the object. Now check this out, I put capital T there, I didn't write of T, but there is an implied T of T there. So this is really different, and it's unlike anything we've actually ever seen before in Calc 1 or in Calc 2 yet. I'm relating the rate of change of this function to the value of the function, not the independent variable. Right, so far, here's the kind of stuff you've seen in calculus. You've seen, oh, the rate of change of t with respect to t is equal to, and then I give you some function in little t, right? Something like that. And then you could just integrate that and find out what t was. So here, this is the independent variable. That's a much more direct relationship. This is not that. This is relating the rate of change to the current temperature. So this is current temp. And we need some initial condition for this thing. So almost all, we need some kind of anchor for the situation. So we have a thing called an initial condition. And I would say t at some initial time is equal to, gosh, I've already used T naught for the ambient temperature. So let's just put initial temperature here. I'll just write it out in English. So let's think about what this is saying, just a little. Let's analyze this equation and get deeply into it. So first off, what happens if T naught is greater than T? So in other words, the oven is hotter than the object. So this is oven hotter than the object. That means this is going to be a positive quantity. Wait, whoa. Did I, hold on. I'm starting to scare myself here. Shit. Take this minus off. We're okay then. Take the minus off. Yep. I confused two different forms of this thing. And I said, we're all good. Life is good. But K here, let's see, is K gonna be? Let's just work it through. So if T naught is bigger than T, this quantity here would be positive. Yeah, then we're okay. Positive, oh, we're all good. Let's leave that alone. Everything's freaking awesome, okay? And then if K is positive, this whole quantity is positive. So this is positive. And that means dt is positive. Then dt is greater than 0. That means your temperature of your object is increasing. I'm going to put a little arrow up for that. Temperature of the object is increasing. If T naught is less than T, then this means the oven is cooler than the object. Or maybe this is a hot potato that I put outside in the winter. So if T is bigger than T naught, that means this thing is hotter than its surrounding. You expect it to cool. So here we have the oven is cooler than the object. And so the object itself will just cool down to the oven temperature. And we see that because this quantity here, what is the sign of this going to be? What will the sign of T naught minus T be in this situation? So here, we've got this. what is the sign of this?
Negative.
Negative, right? Yeah. Because say this is like 1 and this is 2, then this would be 1 minus 2, it would be a negative quantity. So this would be negative times a positive. The whole thing, dt dt, would be positive. Negative, excuse me. So negative. So then dt dt is negative. And so the object is cooling. What happens if the object is the same temperature as the oven? What happens if T naught is equal to T? They're same temperature. 0 here, right? So then I get a 0. And what's the rate of change? 0. It doesn't change. So it stays constant. That's actually an equilibrium state. So if T naught equals T, then when we have dt dt is equal to 0, and there is no change. And we could actually, let's just introduce this term. We're going to talk about it a lot. We're in equilibrium. So this is one of the fundamental equations of thermodynamics. Does that sound right? Yeah. Anybody taking thermo?
I've taken general chemistry, what you learn.
Where you learned this?
Thermodynamics, yeah.
Awesome, awesome. Do you actually talk about this differential equation in there?
Mhm.
Oh, fantastic, beautiful. I'm saying real stuff. Look at that. Let's look at a couple other examples. We're not going to solve this or do much more with it right now. I just want to introduce some examples for us. Here's a really common one. Let's let A of T equal the amount of money in a banking account, of money in an interest-bearing account. You know how interest works? The more money you get, the more interest you got, right? You get a constant rate of interest, but the more you have, the more actual change you're seeing. You gotta have money to make money. That's what this equation's about. The more you got, the more you make. So the rate of change of your amount of money in the account is equal to, let's put a nice solid here. Let's say my rate of interest is 5%. Boy, that would be sweet in a long-term account these days, yeah. So 1.05 times my current, 0.05 times my current amount. That other ways. So this is like a 5% increase in interest, or a 5% rate of interest. So what do I mean by that? Let's take a look. And this is for continual compounding. This isn't like I get quarterly interest. This is like every single instant I'm getting more money. There's a computer running. What's your new interest? What's your new interest? What's your new interest? Adding it back into the account. So for example here, if I had $1,000 in the account, the rate of change dA dt is going to equal what? 5% of 1,000, that's $50. And this K, this A here, or this constant is actually got like a units on it, so it should be, this is like dollars per second or something like that. So I'm getting like $50 per second. If A was equal to just good old $10, then I'm making 50 cents every single instant. Then dA dt would equal 50 cents per second. So the rate of change, the amount of money you're getting every second, is completely dependent on the amount of money you have. This model works for so many damn things though, not just interest. It also works for radioactive decay, or the growth of like a bacterial population. So let's take a look at this equation in a radioactive decay situation. So here's a radioactive decay. let's talk a little bit about how radioactive decay works. I think that'll be a good thing. Like money, we kind of all know, but radioactivity is a weird thing. So radioactive decay, do we know what half-life, when I say half-life, what I mean by that? I'll make sure everybody does. So if I have amount initial A, and this is a radioactive substance, then after its half-life expires, this is a really long time generally. Somebody know any half-lives of like iridium or anything?
The half-life of carbon is 114?
How many? What, more than 14 what? Years? Must be longer than that. There we go. There we go.
What?
She's looking it up.
Half-life of carbon.
There's a 14 in there.
Yeah, carbon 14.
Yeah.
We need a radioactive.
5,730 plus or minus 40 years.
Yeah.
Ooh, let's put that here. So 5,000, what is it?
5,730 plus or minus 40.
Okay, we'll just go for that average there. So this is radioactive carbon. Okay, C14, is that?
Yes.
I don't know, how do you write that? Like that?
Yep.
Yeah, sure. Why not? Whatever.
Fair enough.
Yeah, no idea. But after 5,730 years have passed, you are down to half the amount you started with. It's just all dissipated. After another 5,730 years, you've got half of this amount. So after another 5,730, you've got a quarter of your initial amount. So let's just take a look here at what's going on. What is the rate of change over these periods? So let's look at our average change in A over the change in T. That's what I want to express in each one of these. So for this first one, let's say I had, we should add some solid amounts here. So let's say I've got 1,000 grams here, a kilogram. Here I've got 500 grams, and then here I've got 250 grams of that substance. So in this first period, I've had a change of 500, so here dAdt is 500 grams lost. Actually, I'm going to put a negative there, right, because that was a decrease, over 5,730. Kitra, you have a computer open. Would you please crank a decimal out for that, please? We don't use decimals in here often, but
So negative 500?
yes, negative 500 over, it's going to be less than a tenth, right? So,
Negative 0.0872. And I'll just stop there.
okay, cool, thanks. And then that's in grams per year. So over that first period, this was my rate of change. Over the second period, where I started with a smaller quantity, here my rate of change, dA, delta A over delta T, is going to be negative 250 over the same period of time, 5,730. And I guess that's just half of this number right here. So that's negative 0.0, or Kitra, would you take half of that for me,
Yeah.
please?
I'm just going to redo it so then I don't
Or
have to
just do
with the
250
decimals.
over,
Negative 0.0436.
thank you, grams per year. So notice that the rate of change in the substance depends on how much I have at that moment. That's the key observation here. So let's put that here. Key observation. The rate of change is literally proportional to, the amount of substance, the amount of C14. And this is true for any radioactive substance. So we can express this as a differential equation, that the rate of change of A, let's introduce some new notation that I'm going to want to use a lot. And you've probably seen this before. I'm going to write dAdt, and that use this A dot instead of a prime. So instead of a prime like F prime for the derivative, will be A dot. That means with respect to T, generally it's like science-y kind of thing. So it's A dot. So A dot is equal to we've got our proportion constant here. I don't know if that's exactly it, but we're just gonna say some negative constant times A. And here this K is a positive number. So because what I want to say is it's decreasing proportionally to A. We would, this K may or may not be related to this number we've cranked out here. And then we've got an initial condition. And that is that A at time 0, we can just say here's 1,000 grams, why not? We would have to find this K by going in and solving this and then figuring out what we have when, and we can find that. But I'm not going to make a claim that it's this estimate that we have there. Okay, so look at how similar the equations are. dA dt is a constant times A. dA dt is a constant times A. If I had a bunch of bacteria, oh, how about this? We have a rumor at Regis, a rumor that, let's see, what would be a good rumor to actually have at Regis? We got an endowment. we heard a rumor that we've got an endowment and we don't have to worry about going under in the next 10 years. Something like that. That would be cool. We heard a rumor that Regis was financially managed well. What if we heard that rumor? Nobody believed it, but we would, sorry, it's just me venting a little bit, just a little bit. So let's say a spread of a rumor. Let's just talk about it real quick. So a rumor starts with one person, and they tell 2 people. And each of those people, and then they tell these people, now look, you've got to keep this more secret than I have. And then they don't. And each of these people goes to 2 people, now look, don't tell anybody, but Regis is financially sound. Okay, I won't tell anybody. Hey, don't tell anybody, but. So, at each step of the way, the number of people who know the rumor doubles. So this is really equivalent to a half-life, kind of, but like it's like doubling growth. It's the doubling period of this rumor. But notice how the rate of change from generation to generation depends on the number of people who knew it. So here, let's just talk about the number of people who know over, let's see, what do I want to say? The number of people who knew? Wait, what do I want to say here? What is changing? How is this? This is like interest. It's just like interest. Let me use a differential equation to think. Let's let R equal the number of people who know the rumor. And, oh, yeah. Notice when 4 people knew it, the rate of change in R was, it's doubling each time. Oh, but the increase in the number of people, right. So from here to here, this is so change in R, that's what I want to say. Change in R in this generation was just 1. Change in R in this generation was now 3 more people. Change in R in this generation was what, how many? 7 more people knew? Something like that. No, this is dumb. Sorry. 2 more people knew here. 4 more people knew here. 8 more people knew here. Because these people already know it. I don't know why I'm subtracting them from it. And then 16 people and 32 people. But the rate of change from over the time period is here. This is an increase of 2. So the delta R here is 2. Delta R here is 4. Delta R next is going to be another 8, we'll learn it. Then delta R is going to equal 16. So this delta R, the change in R is moving along with the number of people who knew it. So I would say R dot, change of R, is directly proportional to the number of people who currently know it. and then r at some time 0 equals just 1 here. Let's just say r at 0 equals 1. This was like the president of Regis and told somebody, and then the rumor trickled out. Sorry, that was a little cumbersome. That was not super smooth. But, oh yeah, can I help with something?
No.
Oh, I'm sorry. We'll keep talking too. I'm not trying to make you
No,
stuck.
no. I figured it out.
You got it? Okay.
Yeah.
Okay. We're trying to read my writing.
Yes.
Yes, that's
But we got it now.
perpetual problem. Yeah. Glad you got it. Okay. So I think that's enough examples. I don't even want to go into any examples. Let's just talk about how to solve these things, or at least understand what the solutions are. Let's go back to Newton's law of cooling. Yeah, let's go to the radioactive decay model. Yeah, that'll be simple. We'll start there. Okay, so solutions to differential equations. So I'm just going to call them DEs, differential equations. And where did I want to go first with that? Yeah. Okay. Oh, we're starting out really simple. So here's the rumor growth thing. So the change in the number of people who know the rumor with respect to t, here's an example, is equal to 0.12 times the current number of people who know it. There we go. So R of t equals number of people who know the rumor. And maybe this is on a national level because we've got some pretty refined numbers here. Who know a rumor. And let's also say that R at 0 is 1. Why not? So what does it mean to be a solution to a differential equation? It means you're a function R of t, whose derivative can be found by just multiplying the original r by 0.12. So check this out. I'm looking for a function r whose derivative with respect to t can be found by just multiplying the original function by 0.12. So I can look at this in this really interesting way, and I'm going to show you the solution here. I'll show you how to find it probably on Wednesday. But if I just put 0.12t right there with a constant in front, this actually solves that part. Now let me show you what I mean. So I claim this is a solution. So I check that. Here's the checking part. Check means I'm going to find dr dt. And that means I have to differentiate this function. What's the derivative of this function? So yeah, you guys got to do stuff now. Sorry. I know that you didn't see that coming because I've been rambling like a madman. What's the derivative of that with respect to t? I guess I can get some tea. I'll get some tea. What's the derivative, friends?
Is it the same thing, but times 1 over the 0.12?
You're integrating.
Oh.
Yeah, but that's okay. That's okay. You're doing calculus, and I'll take that any day. That's great. Remember how we take the derivative?
Yeah.
So we're so used to integrating, you're going to probably accidentally do it. But if I want to take d dx of e to the f of x, that is the derivative of the exponent times e to the exponent, right? So that rules what I'm using here. Yeah. So you're thinking right, Kitra. But it's much simpler. It's just the derivative of 0.12t. So it's equal to d dt of 0.12t times ce to the 0.12t. And what's that? Yay, thank you. Cool. So 0.12 times ce to the 0.12t. So look, dr dt is this formula. But notice that this is actually just R again. R is right here. It just showed up again. This is R of t. So this equation here actually does say that dr dt equals 0.12 times the original R of t. So this is a solution because it makes that equation true when I take its derivative and plug it in there. Now I've got that initial condition. The initial condition is going to help me find C. So let's make a little note of that. This is called a general solution. And that means we haven't taken into account this initial condition yet. The particular solution takes the initial condition into account. So we need R of 0 to equal 1. So that means I'm going to go to my formula that I just came up with. So let t equal 0, and R of 0 is equal to 1 means that 1 equals C e to the 0.12 t. I'm just taking this formula and plugging 0 in for t. Oops, I mean to do that, I didn't do that. What's e to the 0? Yay, thank you. So C is just 1, because this is equal to 1 right here. So C equals 1, and my exact solution for this thing is R of t is just e to the 0.12 t. That's our solution, including the initial condition being satisfied. Still satisfies this rhythm of derivatives and satisfies this more particular piece of information here as well. Let's take a look at another one. Let me see, is there any questions on that? For sure, let's talk if there's anything at all. Yeah, we're good? Okay. Did you have a question, Vivian? I feel like maybe. No, okay, got it. Let's look at something a little more spicy. Here's another differential equation. X double dot plus x equals 0. What does x double dot stand for, you think?
It relates to 2 things instead of 1.
So say that again?
It relates to 2 things instead of 1.
Does, what things?
2 derivatives.
2 derivative levels, yes, absolutely. So this is the second derivative. So this is actually d squared x dt squared plus x equals 0. Let's verify that a solution looks like this. Claim. I don't have any initial conditions here, it's okay. X of t equals c1 times cosine of t plus c2 times sine of t is a solution for any c1 and c2 constants. So let's check. That means we have to find the second derivative of this. Let's do that together. Your turn. Good practice. What do I need to translate, Kelby?
No, nothing.
You got it?
I'm just blind.
Well, and the two of us together then make a bad pair, right? Because this is not exactly accessible writing, I would say. So we got to find x dot, find that, and then find x double dot. Let's just make sure we can find those okay. let's just make sure we all agree on that second derivative. Got the sign changes and everything in there, right? When cosine goes to sine, it flips from a flip sign, SIG. So, once I've got this, all I have to do is show that when I add it to the original x, they cancel each other. This is saying the second derivative of x plus its original state cancel. That's how I read that. Or another way to read it would be this: x is equal to the opposite of its second derivative. Notice I can just move that around, another way to say it. And you can see that that's true because let's just copy the original x here. And when I add those together, I get x double dot plus x equals cancel, cancel, 0. So this is actually, if you take DiffEq with me at some point in the future, this is a model of a mass spring system, actually. And you could write it out like this. When you write it like this, x double dot is equal to negative x. You can think of this as the acceleration of, well, take a mass spring like this. You've got a mass on it. And then you pull it down and just let it vibrate back and forth. So this is equilibrium. I extend it past equilibrium. And let's say so here's equilibrium right here. And then I take it and I go to an initial condition. So I stretch out the spring. And then I release it. And what's going to happen is it's going to come back, go up, compress the spring, right? So it's going to come back, it's going to reach equilibrium at some point, and then it's going to compress the spring into a tighter state. And then that spring and gravity is going to pull it down, and the spring force is going to force it down. And then it's going to be like this. And then it's going to come down to here, to where, if there's no friction, it's going to come back down to where I originally displaced it. And then what I'm going to see is this continuing over and over again. And this is analogous to, this is the acceleration right here. It's the second derivative with respect to time of position. Wow, Excel, just stop saying it right there. But this is the acceleration of the object. And it's proportional to how far it's extended. This x equals the extension here. So anyway, we're not going to go into deriving that, but that's a really nice differential equation. Let's look at another one for solutions. Here's one. Let's go back to that Newton-y thing. So here's another example. And I'm going to ask you this to find it. I'm going to give you 3 choices. So I've got v dot equals 1.5 minus 0.5 v. Which are solutions? You might be able to eliminate some of these easily. So 1.5t minus 0.25t cubed. V is just equal to 3. V is equal to 3 plus 2e to the negative 0.5t. And then V equals 3 plus c e to the negative 0.5t. I ask you, it's a little quick quiz with no karmic debt. Which of these are solutions? And you might be able to do it in your head, some of them. And all you have to do is take a first derivative and check. Not all of them will be obvious, I think.
Are there multiple solutions?
Yes, there are. There are multiple right answers here, Lou. Yep. You got it figured out?
Yeah.
Answered your own question? Cool. Awesome. You doing this in your head? Yeah?
Try.
Yeah? Cool. What are you thinking? certainly looks too complicated to be a dupe, doesn't it? Kind of, but also, yeah.
Bring the like 0.5 down 1.5 by the can.
Yeah, definitely.
But you said there's multiple solutions.
Yes. Yes, let's label them A, B, C, and D. So that we have an anchor. You think you got it? Yeah, okay. Okay. Start cranking out derivatives and so forth. So you just need to crank out both sides of the equation. So crank out V dot and then crank this quantity out and see if they're the same. And that'll tell you if you've got it or not. Yeah, it's. Can we see that A is not a solution? Is that showing up? Make sure that you see that. This is 1.5 minus 0.5 V. If V is this, turns into this god-awful thing. But V dot is just this, and that ain't that. This doesn't even have a T squared in it. Does that make sense that that's not a solution? And if it doesn't, let's talk. Really important to understand this point. Is that looking okay, Kelby? Yeah, cool.
Why is
Because I took the wrong damn derivative. No, I did. No, I took the right derivative because I was saying, so I was claiming, is this a solution, Vivian? And I just took its derivative with respect to t. So that's just 1.5, and then power rule here, that 3 comes out in front. And that goes to a t squared. Yeah?
And then you take the given V dot.
Yeah, and then just plug that into the other side and see what that turned into. Fernanda, is this, yeah? Good, yeah. Daniela?
So let's try and process it.
Cool, do you want me to talk it through again?
I'm just confused about like the second half.
This part here?
Yeah.
Okay, so I took the right side of the equation. It says take 1.5 minus half of the V function. If this is V, that's what I'm going to replace that symbol V with, this whole expression. So I took 1.5, this thing here equals 1.5 minus a half, and I literally just plugged that formula in for the V. And then I just simplified. And it turned into this big mess here. Does that kind of help as how I got it?
Yeah.
Yeah? Okay. Is this a solution?
No.
Are you sure? What's V dot? What's V dot if V is just constantly 3? What?
Oh, I was adding them together.
No, that's okay. Yeah,
Oh,
so
yeah.
you're doing more work than you're doing something different than I'm asking, Jackson. I think it's probably right. But what if V is 3? What is V dot? 0. It's not changing, right? It's constant. So for B, V dot equals 0. When I plug 3 into the right side, I get 1.5 minus a half of 3. That's 0. So this is the V dot, and then the right-hand side, let me just put it, maybe write it like that so it's a little clearer, is going to be 1.5. So again here, I'm using V is constantly 3. So minus 1.5, 0.5 times 3, that is 0. So that is a solution. This is a solution to the problem. It's a constant solution. It never changes. You could think of it as an equilibrium solution. It works, and it never changes. Now, when I was talking to Ms. Kitra earlier, she was thinking these looked like possible solutions. Let's check them together. So we go to C. V dot, I'm going to figure out what that is. That is 0 minus half of 2, which is a 1, e to the negative 0.5 t. So I just differentiate that with respect to t. And then the right-hand side of that equation is going to equal 1.5 minus 0.5 times the v. So I plug that whole thing in. And then I simplify. So that's 1.5 minus 1.5 plus e to the negatives, minus e to the negative 0.5 t. Do I have a solution? These cancel, and I'm left with the right-hand side is equal to negative e to the 0.5 t. That's the derivative. So the left-hand side, v dot, is equal to the right-hand side. So this is a solution. And let's make a note on B. This is a solution. And then D. D is pretty much almost the same. Well, let's check it through. V is going to turn out, D is a solution as well. So when we crank out V dot, we're going to get 0 minus a half C e to the negative 0.5 t. That C stays in there. A negative 1/2 comes out in front. The right-hand side is going to equal 1.5 minus a half of my claimed solution. I write that whole formula in. And you can see here that this is going to work out because I'm going to get 1.5 minus 1.5 minus 0.5 c e to the negative 0.5 t. These cancel, and I got the same thing as I did when I took the derivative. So this is a solution for any c. So this is a solution for any c. That's why 3 is a solution. Because if c is equal to 0, it's just 3. This works, if you prove this is a solution, you get this for free and this for free. They're both special cases of this. That is one way to understand what a solution is. That's a quantitative way. So all this stuff is quantitative. We're doing computations, and things are precise. We're also going to talk about qualitative. This is the fun part. This is the part I really dig, the qualitative side of all of this. So before I go on, let me just stop. Is there anything you'd like to talk about here? Anyone? You feel okay on that? Okay. All right, let's stick with this equation. I want to show you how to understand this in a whole different way. We've got like at least 3 different ways to understand differential equations. So this is the tangent slope. Tangent slope to a solution curve. Right, if I said, oh, hey, v of t is equal to this, and then I said, find v dot of t, this is your equation, this is your slope equation. So one way to look at this is the slope at some point can be computed with this formula. So let's rewrite this. So you could write this as the slope at a point t comma v is equal to a slope of tangent, slope of the tangent at a point tv is equal to this formula, 1.5 minus 0.5 v. So I can look at this thing as just slope information of the solution curves. And this gets fun, because we can make a really cool picture now. So we can make what's called a slope field or a direction field and understand the whole of all the solutions for this thing quite well, like at once, at a glance. So we make a slope field to gain a qualitative understanding of all solutions. So what I'm going to do is get out, just like I was about to plot the solutions, I make a TV graph. Oh yes, T and V here. This is my V axis, V of T axis. Here's my T axis. And what I'm going to do is go to every single point in the plane and plot a little line that looks like a tangent slope using this formula. So again, this says that my tangent slope is equal to 1.5 minus 0.5 v. It only depends on the v coordinate of the point. Notice it doesn't even know what, it doesn't care what the t coordinate is. So, if I said, what is the slope of the tangent at the point? So let's make a little chart here. Point, slope. So at the point 0, 1, which is right here. What is the slope? Well, I go to this formula. The slope is, now again, remember this is TV. So the slope, m, is equal to 1.5 minus 0.5 times the v value times 1. So that's just 1.5 minus 0.5, it's 1. Any solution that goes through this point has a tangent slope of 1. So I'm writing m equals 1 right there. So if I had a solution to this thing, and it passed through that point, this is the tangent curve at that point, or the tangent to the curve. Let's check out another one. What happens at the point 1, 1? So let's make that 1, let's make that 1. What is the slope at 1, 1?
It's still just 1.
It's still, what's that?
1.
It's still 1, right? Because all this depends on is the v coordinate. So you're right, Kitra. M, here we still have v as 1. Same slope. I feel like my voice is dying. It sounds like it. I'm going through the change. Second puberty. Reverse puberty. I'm going back into the ground. So I'm at this. Here's where it changed the first time. Here's now the new time. Parabolic arc of life. All right, so at 1, 1, the slope is the same. What's the slope at 2, 1? Same, right? In fact, the slope is 1 anytime v is equal to 1. So all along, v equals 1, the slope, any solution that comes through that line has a slope of tangent slope of 1. All right, what about Let's go to 0. What if v is 0? So let's say, what about through 0, 0? What's the slope at 0, 0? 1.5, do we see that? Yeah? So slope m is 1.5 minus half of 0, because that's the v coordinate. So it's just 1.5. So the slope here is a little steeper. Can you see that it won't matter? And I'm going to make it look a little steeper. That all along v equals 0, that's the slope. So all along the entire t-axis, the slope is 1.5. So make it look a little steeper than the thing above. This gets tricky. But that's supposed to be steeper than that one up there. It kind of looks like in some places less than others. What is the tangent slope at 2? What'd you get? 0.5? Yeah. So when v equals 2, so now we're getting a little smarter here. We realize it doesn't matter what t equals. So on the line, v equals 2, m is equal to 1.5 minus a half of 2, and that's just 0.5. So it's less steep here. It's half the slope, so m equals a half. So I'm going to write m equals a half there. I'm going to write m equals 1 here. I'm going to write m equals 1.5 here. What about at v equals 3? 0. Cassie, you were ready for that one. So at 3, all along v equals 3, m is 0. So here, you just, the arrows, I'm going to put arrows because we stay flat on that curve. The tangents are all horizontal. We're starting to see a flow appear in the plane. So you can kind of think of this as currents. Imagine this was a table that was laying down, and these were just currents of water flowing. And we can put little arrows on here because time flows to the right. So these are actually kind of trajectories, is a way to think of these as well. And right now, I'm getting a sense that a solution to this thing might look something like this. Come on, be good. Not good. Be good. Yes, better. That a solution to this thing might look something like this. And it's got to have the tangent slope of 1.5 when it crosses that, a tangent slope of a half when it's there, tangent slope of that, and then it becomes maybe asymptotic to that line, y equals 3 up there. Now remember what our solution, one of our solutions looked like? It was 3 plus, what was it? What was one of our solutions originally?
3 plus 2e to the negative 1/2.
Thank you. Like that. We haven't quite, that's actually one that, this is a little bit more than 3, right? Because this is a positive number. E is always positive, the output, and this is positive times 2. So this would actually be above 3. One of the solutions below 3 would probably look like this. And think about what's happening. As t gets bigger and bigger, what happens to this quantity? What is the limit on this as t goes to infinity? What's the limit on e to a negative something t as t goes to infinity? You write it like this without a... What's the limit on that as t goes to infinity?
0.
0, right? So it's going to 0. So check it out. As t goes to infinity, this v solution goes to 3. And that's what I'm seeing in my guess up here. What was another solution that we had? We had v equals 3 was a solution. Look what happens when you start on 3. It pushes you to the right. You never leave that. This is an equilibrium solution. You stay on this line right here. Now, if we did this above, like we went to 4, I don't want to do it. You could probably figure it out. Yeah, when v equals 4, what's our slope going to be? negative a half, right? So 1.5 minus half of 4 is 2, so negative a half. So along this line here, we've got a slope of negative a half. And do you see the mirroring, the symmetry that's kind of occurring here around this? Got this lovely herringbone thing going on here. And if I started above and followed all those slopes, I would get a solution that looked like this. So I now actually understand every possible solution just by getting these tangent slopes in there. I know that no matter what happens, it's going to act like this. Every single solution would have to do this. And we now understand the entire set of solutions simultaneously, one glance. It's freaking amazing and beautiful. This is an equilibrium solution. So this is an equilibrium state right here. And this is actually a Newton's law of cooling, just in a slightly different form. But this is called an equilibrium solution. What would happen? So let's think I'm on this. I'm cruising on this, I'm riding some little ship along these currents. What happens if I got bumped off above? What would it do to me? So I'm riding along, I get bumped off a little, some wind blows, knocks me up here. What happens to me? Head back to the equilibrium, right? Do you see that? Do you see how the flow on top pushes me toward the equilibrium? The flow on the bottom pushes me toward the equilibrium state? This is a stable equilibrium. Because if you move away from it, you are brought back to it. Stable equilibrium, they're all over the place. Stable equilibria are something like this. And this is also going to be like a big deal for us. So here's an equilibrium state. That's not bad, right? Highly unstable. But it's an equilibrium state. Are you just like wickedly impressed with my ability to balance pens? Yeah. And then this is also an equilibrium state. And when I veer away, it comes back. This is a stable equilibrium. You're always brought back to it by the physical properties of the system. This, clearly I just want to show that I can do this again. Shit! No, I can't. Okay, well that's on camera. I need a bigger one. Let's see. I used to do it as a kid. I used to do this a lot for some reason because I was a kid. But hey, how are you? Close talker. Okay, there we go. So that is a unstable equilibrium, incredibly unstable. Can I push? Do you think I can toss it and catch it?
Try.
I'm gonna try. Hold on. Oh, okay. Okay. Fuck it. All right. Wait, one more time. One more. Last one. I think I need more for this for stability, right? Like. Class is over. That's it. Thanks, kids. Oh, thank you. Oh yeah, please take a picture of the beautiful leaves floating on.